Okay, here we go. So first lecture of the semester. This is an introduction to chemistry. So what is it? It's the study of the composition, properties, and transformations of matter. That's the definition of chemistry. Why we want to study this subject? It can be a tough subject, but it's the foundation of all living and non-living things. Okay, so everything that's considered inorganic and organic is made up of the elements. And as far as we know, everything in the universe is made up of the elements. The difference between physics, chemistry, and biology, in my mind, is just a matter of scale. Biologists study bigger things like cells, organelles, tissue, that kind of thing, organs. And chemists study molecules, atoms. But if you look really closely at a cell, or if you look really even closer at an organelle, you get a more powerful microscope, you're going to see that those organelles are made up of biomolecules, and biomolecules are made up of atoms or the elements. Okay, so chemistry is really important. In fact, my background is in drug design, and so chemistry is everything when it comes to drug design. We have to build little molecules that interact with our biomolecules and inhibit certain functions in our bodies. Just going to talk about a little bit about the scientific method. You might have heard about this or even studied it in a different class that you've taken already, like a biology class or something like that. I'm going to go through this really quickly. Basically, scientists do this. They ask questions, okay? So there's lots of questions still to ask, even though a lot of the major concepts, at least we think we've solved most of the major concepts like quantum mechanics and classic physics and this kind of stuff. But we're still asking questions, okay? What's the question? Why is the sky blue? That kind of thing. So I've got a question. I'm going to gather information and resources. I'm going to go see what people have already done related to my question. Based on my research in the library or wherever people go these days. Actually, these days it's the internet. Back in my day, we went to the library and we had special science indexes that we look through and then dig up journal articles. Nowadays, it's easier than ever to do research. Hypothesis is an educated guess, okay? In everyday language, we use the term theory to describe, I have this theory or whatever. What people really mean in everyday language is they mean a hypothesis, okay, not a theory. Because a hypothesis is an educated guess. We're not sure of the answer yet, but we have a reasonable guess as to what's going on. Okay, theories, those are different. We'll talk about those. Plan some experiments, okay? So we think we know what's going to happen, but let's plan the experiments, get the equipment we need, then do the experiments, collect the data, analyze the data. That's often the hard part of my own research. Analyzing the data was the real challenge. And then interpreting the data, drawing conclusions, and then communicating the results. We still publish in scientific journals these days. The most famous scientific journal is called Science, at least in America. In Britain, the most famous journal for science is Nature, if I'm not mistaken. And then chemistry in this country, the Journal of American Chemical Society, or JACS for short, is the premier chemistry research journal, but there's all kinds of chemistry journals. Journal of Organic Chemistry. I subscribe. A lot of people on YouTube say that. Subscribe to my channel. Subscribe with a B. Subscribe to the Journal of Chemical Education, and I get a lot of useful information out of that journal. Okay, so that is the scientific method. Now let's talk about theories. So I mentioned this earlier. Most people, when they say I have a theory, really mean a hypothesis. What a scientific theory is, though, is that it's a set of hypotheses that all come to the same conclusion and they're formulated into a theory. Okay, so we've got a really good working understanding or a really good understanding of the facts and interpretation of the facts. They are not guesses. Okay, so that's why I don't like the way people use this in everyday language, because they're implying that they're guessing at something. Scientific theories are not guesses, okay? They're not guesses. They are dynamic, though. They can change over time. In fact, one of the fun things that scientists do on a regular basis, they get together in conferences and give talks and kind of debate each other and kind of pick apart their theories. But it's very helpful, actually, and scientists love it. In fact, theories just get better when we go to conferences. They change a little bit, but only for the better. Okay. Examples. In this class, we'll talk about atomic theory, just some basic atomic theory. We'll also talk about some valence shell electron pair repulsion theory, VSEPR for short. Gravity. We won't talk about gravity, but gravity is a good example of the difference between a scientific theory and a law. Let's take gravity, the law of gravity for a second here. The law of gravity the law is a statement of fact. If I hold a ball in my hand and I tip over my hand, the ball is going to fall and hit the floor. Okay. That's a statement of fact. Actually, we're pretty sure that's going to happen. That's a law of gravity. The theory is the explanation, basically. So how does gravity work? Well, that's the head scratcher part, actually. We still, as far as I know, I'm not a physicist, but as far as I know, we still don't have a supremely deep understanding of how gravity works. So in other words, the explanation, the mechanism of how gravity works. Okay. But evolution, on the other hand, is a different story, actually. Evolution, I'll say this, maybe some scientists would dispute this, but I say it's both a fact and a theory. It's a fact because we know organisms evolve over time. They do. Take the COVID-19 pandemic. That COVID virus evolved quite a few times and became resistant to certain vaccines that we released early on. It just, small things just evolve quicker than big things. Elephants evolve much, much slower than viruses do. Okay. And but it's a fact. I mean, they basically evolve. Okay. We're very sure of the facts. Okay. The interpretation of the facts is where we have still some debates, but we're pretty confident we understand the mechanisms of how evolution works. Okay. Through, mutation and selection and this kind of stuff. So I'm not a biologist, so I don't want to get it. I love the topic of evolution, but I'm not a biologist. So I'm going to get myself in trouble if I start throwing out terms that I don't fully understand here. Okay, so scientific laws, I mentioned this already. A law is different than a theory. A law is a statement of fact. Okay, so gravity predicts a ball is going to fall out of your hand and hit the floor. Okay, that's a statement of fact. Is it's unreasonable to think that that's not going to happen if we do that. Okay, in this class, we're going to talk about the laws of thermodynamics. We'll mostly focus on the first law of thermodynamics in Chemistry 1B. Let's see, this is 1A. So I thought for a second we were in 2A. 1A, you'll take 1B eventually, and you'll talk about the second law in that class, but our class, first law. Law of conservation of matter and energy. That's the basis for even balancing chemical equations. So very important. Law of gravity. You'll talk about that in your physics class. Okay, so this first lecture is going to be real short. We're going to wrap up on states of matter. So earlier I told you that chemistry is the study of the properties and the transformations of matter. What is matter? Matter is the stuff of the universe. As far as we know, everything in the universe is made up of the elements. So matter is stuff, okay? Matter can come in three principal forms. It could be a gas, it could be a solid, it could be a liquid. There's a fourth state of matter too. It's called a plasma. It's just not very relevant for our discussions in our class here, but plasma, think like really hot stuff like the sun, okay? Okay, gases have changeable shape and volume. So if I describe a substance, some matter as a gas, it has a changeable shape and volume. Solids, if I describe matter as a solid, it has a fixed shape and volume. And then liquids have a fixed volume but changeable shape. If you could look through anything, any substance through a very powerful microscope, and if that substance was a gas, you'd basically see this. In the container that's holding the gas, you just see a random distribution of gas particles that are all over the place. And they are not stationary, they're always in motion, but they're well separated from one another. In fact, if you could see these gas particles through a powerful microscope, they would look like way separated. Okay, there's a lot of empty space between gas particles. We assume that there's no force of attraction or repulsion keep them together. So well distributed and moving around in random directions. Okay, that's not true for liquids. Okay, liquids, let's just take water as a good example, obviously. So in liquids, if you could look through a very powerful microscope, you'd see that water molecules in a liquid are pretty close together. In fact, there is a force of attraction between these little water molecules. But beyond that, they don't really have an organized structure yet, but they are very close together, and there is a force of attraction holding very close to one another. And so you have to break that force of attraction between the water molecules to get them to go up into the gas phase. So unless you provide enough energy to break what we call intermolecular bonds, they're going to stay a liquid indefinitely. Okay. So a little bit chaotic, but they're real close together. They're kind of essentially glued together with intermolecular forces. And then finally, solids. So solids, you have a fixed shape and a fixed volume. And if you look through a very powerful microscope, you'd see that the particles that make up whatever solid you're looking at are highly ordered, especially if we're describing the solid as a crystal, and they have very fixed positions in that solid, okay? Are they totally static? Are they totally stationary? No, actually, they still have a little bit of energy, but they're not moving around. They're not translating too much at all, if at all. But they are like, they do have energy. They are vibrating if depending on what type of substance we're talking about, but they do have a little bit of energy. They're not totally motionless. So fixed positions, very ordered. Okay, so those are your basic 3 states of matter with differences. Physically speaking, they're different in the sense that gases are just random. They're all over the place. Liquids, they're very close together. They're glued together, but in sort of like haphazard ways. And then solids, very ordered structure. Okay, states of matter. All right, I told you this first lecture is going to be real short, and I think we're going to save the next topic, classification of matter, for a different video. So that's it for this introduction.